Hi everyone, dear friends, let's start our seminar. So in this seminar we'll take a look at learning and we'll learn how to build a neural network for the images recognition, and we'll compare this module with the fully connected neural network. So let's start, and first of all let's describe the data set that we're going to work with. So first of all, let's look at this program and this type, which is called CFR10, and it has several types of recognition. So image recognitions like planes, birds, and so on. So these pictures have resolution of 33 by 33. Therefore, it's quite easy for us to use it to build and to recognize them using the convolutional neural network, which we're using today in our class. As previously, we'll use PyTorch library. So yeah, but let's start slowly one by one, and the first task will be to upload the dataset. So I've already worked with all the files, therefore basically I will just show you the result and then make comments on the progress. So let's look at the first square. So there is nothing clever here, just the import of libraries. First of all, let's start learning about uploading the files into the library. So we upload both types of files, learning files and test files. So here we have a parameter which is called train. So yeah, if we have true result, then it is true, or we have if it is wrong, then it's a false. So here we don't mention any transformations. We just mention that we need to change this picture into a tensor. So also here we need to use the field called root, so that will understand where we are saving the data, the results. So yeah, sounds good. And now let's create data loaders or data clouds. I hope you remember information regarding the data loaders from our previous tasks, because we've talked about it before. So yeah, let's create two paths for test files and train files. So we will call them test loader and train loader. So therefore we upload train data into this train loader, and in the second test folder or test loader we use the test data to test. So yeah, please note that in train loader we upload 16 objects, which equals the number of objects for the training sample. And yeah, for the test loader, so yeah, we can also keep the batch size of 16. So yeah, both batch sizes are 16, so we won't have any hurry, any troubles. So test data and train data will be also sent into the testing model in the same way, in the same number. So in the test loader we'll also make the shuffle false. Therefore the data will come determined during the training. And yeah, let's take a look at test data. This is such object of dataset. So it has 10,000 objects, 10,000 pictures. We don't make any transformations with pictures. So sometimes it happens when you work with data classification. So the selection is artificially reasoned. So it means that the dataset has been manipulated a bit and transformed. So it helps to improve and to make the training sample bigger. So in this case we won't do it. This is an additional task marked with an arrow, so like a special task. So yeah, now let's take a look at the data. Let's see what is there. So here we create a new iterator from the train loader. This iterator will work with training data. So we upload the batch with 16 from the training data. So then let's look at the pictures, and each picture has 3 channels in this batch, and the size of the picture is 32 by 32. So therefore in tensor with images we have images, and we have labels in tensor with the labels. So let's take a look at the example. So there is a quite easy function. You can take a look at it yourself. And here we have different pictures with deers, cars, dogs, and horses, and so on. So this is our data set and all the marked files. So now let's create a dictionary with labels. So it will help us for testing purposes only. Let's import several functions for neural network to learn. So these are the standard functions which you've worked and imported previously. So you can find all the objects for neural network to learn at torch.nn. Torch.nn.function has all the functions for neural network development. So for example, the activation function. So let's take a look at the difference between the way how to build neural network in comparison to actual machine learning algorithm. So the thing with neural network is that it gets data with batches. So there is an option for neural network to read each data set and to deduct it from tensor and from verses. So therefore we can do all the different deductions and calculations with a neural network at the same time. So yeah, this simultaneous work gives us an advantage to work with video cards, because video cards also have the same option of working simultaneously and calculating data, working with data simultaneously. Therefore, if we teach neural network without a video card and with video card, these are two complete different stories. So therefore, as I said in my lecture, Alex Krzyzewski won with his neural network AlexNet. And I told you only about the architecture of this network. Therefore, we can think that Alex has only invented the architecture of this neural network. So, however, the architecture that he has proposed was quite essential, quite common, even for that time. However, he was the first person who understood that you should learn or teach neural network using the video cards, so it will accelerate the process. Because yeah, until 2010 there hasn't been any technologies and hasn't been any, people didn't understand that you can learn using video cards. So yeah, also the team that won there, they understood that they can use the function ILU instead of sigmoid function. So sigmoid function has several problems when it works with images. ReLU function helps to keep the gradient constant. Also, it hinders the gradient attenuation. So we'll talk about this process in the next lecture, on the following lecture. So I'd like to pay attention to the fact that we're using graphic processing unit. So we can check it quite easy using this click the execution environment. So we can click on the link, change the environment. And yeah, as an accelerator, here we have GPU. So there are several options, but we chose GPU. This is good to understand. So if you have chosen accelerator none, then please switch it to GPU and start over. So yeah, therefore we'll also use GPU. If you want to use the better GPU, please click on the instruments. So yeah, please click, then you have settings, and then you'll be offered to buy a Collab Pro version. So this Collab Pro will offer you the acceleration of your video card. So yeah, and we'll move on. We'll look at the fully connected neural network. Later on, we'll compare fully connected and convolutional neural networks. So here we have a very easy class that helps us, so it's called flatten. So I'd like to pay your attention that it goes from the abstract class called nn.module. So in the sense, we will say that this class will inherit and will be used in our neural network as the new one. So yeah, this class will be a small brick in our neural network. So therefore, each convolutional layer and each layer will be a module as well. So in this module, we're interested in the function called forward. So each module has forward function. Forward function. So, and here we predetermine this function. Here we don't do anything clever, we just use the metrics, and we use this formula to make a vector out of these pictures. So we just take all the numbers and we write them down together one by one as one vector. So yeah, we need this function in order to create a vector, so from a picture, and to use it for the fully connected neural network. So our neural network is built in a class called SimpleNet, which is also inherited from the other module. So as we can see, each object in neural network could be a module. So this is top-level abstraction that we're using while we're building a neural network. So this module has an init function. So this function creates all the variables that we're going to use in that module. We create a layer called flatten and we put it in the self. We create two fully connected layers. So the first fully connected layer accepts the picture. So this picture is 32 by 32. So in the exit layer it is 256 neurons. So the second fully connected layer has 256 entry neurons and 10 exit neurons. In addition to forward function, we use softmax. So we use it to the data array, and in the end we have the neural network data. So let's take a look at the forward function with more details. So as an entry data we have x with the tensor of 32 by 32. We use flatten function for this one. So yeah, we make it flat and then we use both layers. So we'll start with the first layer. It is self fully connected 1 and we add x. So yeah, later on we use reloop for this layer. So we shouldn't forget about the activation function. Then we do the same. We add the second layer. So here we don't use reloop, we use softmax function. Therefore we transform the measures of belonging to one of the classes into the probability of belonging to one of the classes. So in the end we bring this vector of probability into the forward function. So yeah, very good. Then here we have this neural network. And now let's take a look at another function train. After we create the neural network, we need to train it. Therefore, we use this function called train. This function accepts a net as an entry data and also the number of training epochs. So here we'll do the training with direct and indirect data application using the neural network. So that we've also done in previous classes. So here it looks quite clear, so we just use the loss function. So it's a standard loss function for the classification. We also use learning rate, here it is -3. So we also know the optimizer. We have an Adam optimizer, so we actually usually use it. So yeah, there is nothing special about it, and if you don't know which optimizer to choose, just choose Adam. It won't let you down. And let's add two arrays, so the learning and the training data arrays. So for the learning or training array, we'll use the results of our training. So for the training array, we'll use this and we'll add a lot of loss functions quite frequently. So for the testing array, we'll actually use it and record only once. So we'll record the loss function only once after each epoch. So we need the test array not just to analyze the graphs, but to understand after which epoch we should stop the training process. So we understand how many epochs are enough. So yeah, let's take a look at our learning cycle. I don't think that there is going to be anything new for you, because the architecture is the same as for the fully connected networks. So we iterate by the number of epochs. So yeah, here we create a new iterator over the training set. So it is called running loss, and here we'll write the compound loss function. So yeah, later on we just go through this whole learning iterator. We use the function numerate, and now we have this number e. And here we also have batch, which is a compound element. So we have x batch and also y batch. So in x's and y's we have tensors. These tensors will help us to train neural network in this iteration. First of all, don't forget to put the 0 in the weights in optimizer. So later on we predict the number of the result using the batch. So we start a loss function which has our predicted numbers and our real training results. Later on we do the reverse or the backward training, so loss dot backward. So there is nothing new, it's all standard. And later on we do the next step of the optimizer. So if we did everything correct, then the optimizer knows the loss and backward function. It can check all the variables correctly, and it can make a step. So into running loss, we can use the loss in the current batch. And yeah, let's see what we're going to do here. So here we need to check the average loss for the previous 500 of iterations. So all losses are in the running loss. It is the sum of last 500 losses during the iterations. So yeah, that's why here we write running loss divided by 500. Later on in training loss we add loss for last 500 iterations. Then we even it up to 0 because for the next iterations we can start over. So that's why it's quite simple code. So therefore in training losses we have losses for the last 500 batches. So yeah, this is basically the result and the results of the learning. So yeah, and now we're doing the same thing for the test dataset. In the test dataset we just need to measure the quality. So yeah, therefore we write torch no grade. Then we start our iterator for the test dataset. And now let's look at it closely. So here we do pretty much the same thing, however we don't do backward in comparison with the training array. And we add on average running loss for the test loss. So we use it for the entire epoch. So here we go through the whole set data enter and calculate the compound loss. And then we're averaging it by the number of the batches which we're using. So therefore we have the array of losses not for each iteration, but for the whole epoch. Yeah, therefore we have less numbers here. And we bring back the network for the testing losses and the training losses as well. So yeah, now it's the most interesting part. So we create a neural network and we teach it using existing data. So we've done everything and now you just need to accomplish it. So we create the network called SimpleNet and we use it to learn on our data based on 7 epochs. So I've learned here, that's why, yeah, let's check out the results. So yeah, let's see what we have here. We won't look at everything, just look at the graph of losses depending on the epoch. So here we can see that by epoch number 7 the losses are stabilized. So the training loss is decreasing, but the testing loss is a bit unstable still. So yeah, looks like 7 epochs are enough. So yeah, actually, honestly, if we want to check it thoroughly, we need more epochs to check that the test loss will not fall further down. However, yeah, we can see it in general that it works. Now we're calculating the accuracy, so the number of recognized pictures in the data array. So dear friends, now let's calculate the quality of the testing array. So first of all, we start an iterator, which will go through the whole array. And let's take a look how we'll calculate the accuracy. So here it's pretty much the same. We create X batch, Y batch, and use forward pass with net forward. And here starts an interesting thing. First of all, we need to take tensor from the GPU. So it could be done with the detach function. So then we need to switch the tensor to the by. And so yeah, the next thing, let's take a look at our vector. So it has the probability for all classes and all vectors. So it is the probability that this belongs to one or another class. And so in order to get the number of classes which we use for the objects, so here we need to use the function called argmax and use it for the first axis. So for example, argmax. So therefore we get in y-axis the probability that the picture or the object belongs to each axis. Therefore in y-axis we have the number of the pictures in our batch. So later on in array accuracy we just write an accuracy score, which takes true y numbers as the entry data and the predicted parameters of classes, which we've just done. And here we just put the sum of all elements divided by the objects in the accuracy axis. So therefore here we get the average number of the accuracy using the whole batches. So yeah, overall it is the general accuracy. As the result, here we can see the 40% accuracy for the fully connected neural network. Actually 41%. So yeah, let's do the same experiment with the convolutional neural network. First of all, let's create it. So yeah, here we basically have the same, so the same class flatten. And let's also create a class convnet. This is our neural network, which is inherited from the module. So yeah, how it is created. So during the first step we have the convolution. So the space of the convolution is 5, equals 5. So in our lectures we usually had convolution of 3, but we actually can use different dimensions as well. We'll have 20 filters overall. So it's not a lot, but our neural network is quite simple, therefore we just use 20. So here 3 means number of cards for the entry. So as here we're talking about the picture in RGB format, we need only 3 for the entry. So yeah, therefore we basically have 3 here. So what does this convolution do? It creates 20 cards. So yeah, and basically as the card is different format, so we need to switch the picture, and in the end we'll have picture with dimensions of 28 by 28. And in this way we have 20 cards. So yeah, let's look at our next layer. The next layer will be convolutional as well. So in the entry it will get 20 cards, but at the exit it will give out only 50 cards. And the size of convolution will also be 5. So here we use a large number of convolution to minimize the picture. So in the same way, this convolution converts the picture from 28 by 28 to 24 by 24. So the next layer is pooling. So and pooling in this torch will be used as max 2D. So here 2D means it's 2-layered pooling. So yeah, probably I forgot to mention it, but here the conv2D is, it basically builds our convolution. And here we use candle size 2, which is the parameter for the window size. And here's what we get as a result. We had picture size 24, and now we have only 12, because the size was divided 2 times. So we also need to add more convolutions, because entry we have 50 cards, by the exit 100 cards. And also the size of convolution is 5. So we use also large convolution because we don't want to minimize the picture too much. because we also want to minimize the number of parameters. So therefore the size was 12 and now it's 8. So later on we stretch everything into a vector, and we add 2 linear layers. So the first layer will have entry data picture with 8 by 8, and 100 is the dimension of our card. So it will be the number of cards, therefore it will be 8 by 8 by 100. And in the exit data we'll have 100 neurons. So the second layer will take 100 neurons and will provide only 10 neurons. So 10 is the necessary number of classes in our work, in our exercise. So here everything proceeds in the same way as in a fully connected neural network. Therefore there is nothing new here, so I don't need to explain further. So the most important thing here is to calculate the number of objects for the entry data. So as we wrote the number of cards for each layer, so the number of exit data, there is not a big problem for us just to calculate all these numbers. So it's quite easy to understand how the forward works. So we just set up the first layer, so conv1. So obviously we add a reloop function as it is a picture. So then we're doing the second layer, also use the function pulling, and also in the end doing the reloop. So then later on we're adding the same way the third layer, and as we don't have any layers, we provide a vector and use the flatten function. So in the previous classes we done flatten in the beginning. Here we do flatten after using all these convolutional layers. So then we add softmax to all our fully connected layers. And later on we do basically the same as we did for the fully connected neural networks, so in the same way. So then we'll use categorical cross function and loss function to teach the neural network. So after we got used to this neural network, so let's announce it and let's teach it as well. So we'll teach it using 7 epochs. So and we won't see the whole process because it takes a longer time for convolutional neural network in comparison to the fully connected neural network to learn. So it means our module is more advanced, and also it takes more cards to learn or to teach neural network with the new data. So here you can see we've used 7 epochs, and let's see what is the result. So here you can see the graph, the quality graph, and we can see that in the end there was no errors, so the errors start diminishing. And therefore we have loss at the level of 2. So we marked test errors as orange line. So let's scroll down and look at the quality. So basically it's 0.47. So if we compare it with the previous graph, so it was 0.41 there, and it is 0.46 here. So it means that there is a slight growth. I would also like to know that we've built this neural network just because, so there wasn't any specific purpose, we didn't set any parameters, and therefore, so we probably made a bit of mistakes with the parameters, so how many parameters should be there. So basically we're not certain about the number of parameters. We could change it and we could improve it, and maybe don't use pooling sometimes. So as the result, this is a lesson, and if we're doing the real neural network, we can add more parameters, and then the quality or the accuracy will be much higher. So we use pooling for 2 parameters or 2 tasks. So to quickly learn or quickly teach neural network, that's what we've done here. So otherwise, without pooling, there could be a retraining, so the module will be much more advanced. So here we have quite large data set for the learning sample. That's why we're not afraid of relearning, retraining, but we're more afraid of the long training process. So yeah, therefore you can experiment with this. So you can probably add more convolutional layers, or you can set the current size lower. So for example, for the first layer you can set it up for 3. In this case you have more control for the dimensions of the picture, and yeah, in the end it will help you to build a better neural network, more accurate neural network. So yeah, I hope you can practice and experiment with this neural network as well. So here we've added some additional materials which are about normalization of the batch. So we've talked about it in previous lectures. It helps us to minimize the relearning process and also to minimize gradient attenuation. So here is the sample or the task for building a neural network that I would like you to propose to